Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. I'm here today with a really interesting student request to analyze and find out some kinematic information for a small block resting on top of a larger block, and when a force is applied to the smaller block, the friction between them also makes the larger block accelerate. So here's our situation. We have this small block of mass 1.89 kilograms that's resting at the left edge of a block whose length is 2.73 meters, and the mass of that larger block is 7.29 kilograms. The coefficient of friction between the two blocks is 0.288, and the surface on which the larger block is resting is frictionless. We're going to apply a constant horizontal force F of magnitude 11.6 newtons to that 1.89 kilogram block, and that's going to set it in motion. And we want to know, how long will it take before the small block reaches the right side of the 7.29 kilogram block? And note that both blocks are set in motion when that force is applied. And then we're also going to find out, how far did the 7.29 kilogram block move in the process? So here is our basic situation, and we want to just go ahead and start with our usual force analysis with a free body diagram for our small block. Sorry that that's actually not quite as straight as I'd like to make it. So we've got a support force, a normal force upward on that small block, and a gravitational force downward. And then we're going to apply that force F to the right that's going to make this smaller block accelerate. And then if we are moving the small block to the right, then there's going to be a frictional force opposing that back to the left. And we know it's kinetic friction, so I'm just going to label it small f K for kinetic friction. So now let's talk about the force diagram for that bigger block. So what might not be immediately obvious, and you're going to have to think about a little bit, is that Newton's third law tells us that the two objects in an interaction experience that interaction, that force, with equal sizes in opposite directions. So if friction between the small block and the big block is pulling backward on the small block, then it's friction pulling forward on the big block that's going to make it accelerate. So I'm going to go ahead and draw as close to the same size as I can and label it small fk for kinetic friction. And then this larger block is going to, of course, experience a gravitational pull. Oh, I forgot to mention that I'm going to label these block 1 for the smaller block and block 2 for the bigger block. So we have a gravitational force downward on the larger block, but then we're also going to have a normal force downward, because remember, normal force is an interaction between the two surfaces, and so the weight downward of the small block is going to cause that block to press into the lower block. So I'm going to go ahead and label, and I'm going to call it Fn1 because it's a normal force from block 1 here, and then the normal force on block 2 from the floor is going to be as big as those two combined. All right, so let's get in here. Let's figure out about the accelerations of the block, because we're going to need that to figure out anything about time or displacement. All right, so let's go ahead and set up Newton's second law for that smaller block. So the net force on block 1 will be equal to its mass times its acceleration. And What forces are contributing to the net force on that block? Well, normal force and gravity are balanced. This is why I use the geometry hash marks to indicate congruence there, because they're equal size forces. And so it's going to be the applied force F minus that kinetic friction force that are going to contribute to the net force on that block, multiplied by its mass and multiplied by its acceleration. Quick note, how do I know the two blocks are accelerating differently? Well, for one, the small block is going to move all the way across the end of the big block while the big block is accelerating. So clearly, my smaller block has got to ultimately be moving more rapidly and gaining speed more rapidly in order to travel that extra distance. All right, so here we're going to be able to solve for the acceleration of this block with the applied force minus the frictional force divided by the mass of this smaller block. But here's the thing, we don't know anything about that frictional force yet. So now we're going to have to go figure out some stuff about, I'm at the edge of my tablet. I'm going to have to figure out some stuff about that kinetic friction force. We're going to recall that a frictional force can be found with a coefficient of friction multiplied by the normal force. So in this case, it's going to be the normal force that block 1 is experiencing, because we're talking about the friction force acting on block 1. Well, what do we know about that normal force? We're going to note that vertically, our block is not accelerating. So vertically, on block 1, the forces are balanced, up equals down. So our normal force from block 1 is just going to be equal to its weight. And of course, our block had a mass of 1.89 kilograms, and we'll use 9.81 for the gravitational acceleration. That was actually given in the question, but I left it off. And so I got 18.541 newtons for the normal force that block 1 is experiencing. So now I can use that back over here to figure out my kinetic friction force. My coefficient of friction was 0.288, and we'll multiply that by the normal force that block 1 is experiencing, and I get a value for the frictional force of 5.339 newtons. So from here, we can now plug in the things that we know back for our acceleration. So the applied force on my small block was 11.6 newtons, and we will subtract from that the frictional force and divide that by the mass of my small block, and I get an acceleration for block 1 of 3.31 meters per second squared. Well, great. Now let's go do a force analysis for block 2. So we'll now apply Newton's second law for block 2. And what's kind of nice here is that the frictional force is the only force that's contributing to the net force on block 2, because the sum of the vertical forces down is balanced by that normal force up. My second block, my larger block, is not accelerating vertically. So it's only the horizontal pieces that matter here. So I have my friction force equals the mass of block 2 times its acceleration, and remember, Newton's third law tells us that the friction force that one object whose surfaces are interacting experiences is equal in size to the force that the other object is experiencing. So I already have that 5.339 newtons that I solved for earlier. And I'm going to divide that by the 7.29 kilogram mass. And as expected, I get a lesser acceleration for that second block. Okay, great. So now we've applied dynamics information to get the accelerations of these two blocks. Now we can actually go apply the kinematics that we know to figure out the time that it takes for the blocks to travel and how far the larger block went. So to start our kinematics work, we're going to need to pick an origin for our coordinate system for our physical situation. So to help us, I have here a larger box and a smaller box that we can move to sort of help visualize and establish what's going to go on. So we're going to start from rest. And as my bigger block is moving to the right, my smaller block is going to be moving with it, but also to the other end. So again, it's going to look like this. Oops, went a little bit too far. So what we can do is start with our initial position, and then our final position, we can see that our second block is going to have some displacement from the start. So I can note the left end of the large block is going to be important, but then also the right end of my large block is also going to be important. And my smaller block has gone not just the displacement of my large block, it's also traveled an additional distance to the end. So we can say that block 1 is going to move the displacement of block 2 plus the length of block 2. So if we write that mathematically, delta x, its displacement, delta x1 rather, is equal to delta x2 plus that 2.73 meters that is the length of the second block. And whenever I'm doing kinematics work, I like to think about position time graphs. So we can think about the left end as the important point to pay attention to, and we can think about the right end of the larger block as an important point to pay attention to, and I'll show you both ways. So let me sketch a couple of coordinate axes for us. So this is x and this is t, because we're going to think about this situation two different ways. So I'm going to need two different sets of axes. So if I want to consider the left end of block 2 as my origin, then I might show the acceleration of my small block. Let me actually grab a different color for that. I might show the acceleration of my small block as a top opening parabola that's fairly steep. I actually didn't quite get that as open as I wanted to. It's a little bit too steep at the start, but that's okay. So I'm now going to know that my larger block's acceleration is less, and I need to figure out what would a position time graph for this look like. And here's the thing. My smaller block is going to end up somewhere out here at time t, and that position is going to be where the right end of my block needs to end up. So really, I need to figure out, where did the right end of my block start? The right end of my block started 2.73 meters to the right of the starting point of the small block. So let me write that. Right end of block 2 started 2.73 meters to the right of block 1's ending point. So I guess really, I can't get to my eraser. Hang on. There we go. Of block 1 starting point. So I guess really it's actually better to think about this as, in one case, we're going to think about block 1 starting position and ending position as defining our coordinate system. And in the other, we'll think about the bottom block. So I'm going to have a much more open parabola, like not as steep as quickly, because block 2 has a lesser acceleration. So this is one way of representing the position-time relationship for my two blocks. And now for the other way to think about it is, what's going on with the right end of block 2. So block 2 is going to start at a position of 0 in this situation. And then block 1 is going to have started 2.73 meters behind. So we'll give it an intercept of negative 2.73 meters. And then somewhere out here, didn't get it drawn quite as open as I wanted, but that's okay. So somewhere out here will be a time that those blocks end up at the right end of the larger block at the same time. So again, we've got two ways of thinking about this, because it also, this ties into the equations that we're going to set up for the actual kinematics. So we can think about block 1 starting and ending position as the important places, or we can think about the right end of block 2 as our important places. So we're finally ready to find the time that this all takes to happen. So we're going to have a position versus time relationship for block 1. And the basic position-time relationship for accelerated motion is, of course, v0 plus a half a1 t squared. And then the displacement for block 2 is going to be something similar, but we'll use v0 t plus a half a2 t squared. And then, of course, both blocks are starting from rest. So v0 equals v0 equals 0 meters per second. And so we're left with, let me go ahead and go back to a little bit of color coding to help with that. So that means delta x1 is just going to be left with a half times its acceleration times time squared. And block 2 is just left with 1/2 times its acceleration times time squared. And, again, we're going to remember that delta x1 is equal to delta x2 plus 2.73 meters, but just for simplicity, I'm going to go ahead and calculate this out to get one expression with everything substituted for delta x1 related to time, and then I'll do the same for delta x2. So we found a couple slides ago that the acceleration of block 1 was 3.31 meters per second squared. So delta x1 is going to be 1.655 t squared. And we'll do the same for block 2. And its acceleration was 0.732. And that means that the displacement of block 2 can be found with 0.366 t squared. And now we're going to remember that, once again, we're going to remember that delta x1 was equal to delta x2 plus 2.73 meters. And now we can substitute in what we just found. So 1.655 t squared equals my delta x2, which was 0.366 t squared plus 2.73. And when I keep solving that, I get 1.289 t squared. When I collect the like terms with the t squared on one side, will be equal to 2.73. And I get a value for t squared is equal to 2.1179. I always like to keep extra decimals until I get to the end and then round at the very last. And I get a time of 1.455 seconds. So one thing I forgot to mention earlier is that we are actually going to neglect the dimensions of block 1 in this process. We're not going to worry about its actual physical thickness. So what we had to do for part A was a force analysis to get the acceleration of the two blocks, and then we can use position-time relationships to figure out the time that it takes our two blocks to meet up at the right end of the larger block. And now we can go on and find out how far exactly did block 2 go. So this part is actually really simple. I probably could have put it on the last page, but B is how far, oops, hang on, erase. How far did block 2 go? Well, we just had a relationship for that displacement, and actually let me clean that up and make it a little bit easier to read. We just had a relationship for, oops, what is going on? There we go. For that displacement on our last slide, 0.366 t squared. And now that we have an amount of time, we can find out exactly how far our block went. And notice that we got 0.775 meters. So what this actually means is that, my little demonstration here of the blocks moving like this, a little bit inaccurate because this has my blocks going pretty much the whole length of the larger block. And in fact, these values are showing us that our block only made it about a third, a little bit less, actually, yeah, a little bit less than a third of its length. So I hope you enjoyed today's explanation of this really interesting and complex student request problem. If you have a video solution that you'd like to see on my YouTube channel, you can email me at physicsproblemrequests@gmail.com. If you have other email assistance that you need, you can use freephysicshelpline@gmail.com, and there is a limit of 10 questions per academic year. If you'd like to learn more about my tutoring services, you can contact me at brandyhevlinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, and you can schedule your free 30-minute needs assessment where we will meet and talk about your needs for tutoring and what kind of assistance you want, and we'll set up your free first 1-hour session. And you can also find me on Facebook. I'm Physics Tutor Brandy. I love physics and I love helping you. Until next time.